Hey everyone, and welcome. Today, we are going on a serious quest, peeling back the layers of reality itself to get a look at the fundamental building blocks of, well, everything. We're gonna unlock the atom. So let's just start with what seems like a simple question. What does an atom really look like? Now, if you're picturing a tiny little solar system with electrons zipping around a nucleus like planets, you're not wrong, but you're also not totally right. That image is just one stop on a long, winding, and frankly, pretty wild road of discovery. All right, so our story kicks off way back in the ancient world with an idea that's stuck around for over 2,000 years. The idea that if you keep cutting something in half, you'll eventually hit a particle that's impossible to cut any further. But, as we're about to see, this uncuttable atom was about to show some serious cracks. And for centuries, that was pretty much the whole story. The name itself, from the Greek atomio, literally means non-divisible. The main theory, which John Dalton really solidified in the early 1800s, was that an atom was just a simple, solid, indestructible little sphere, kind of like a fundamental billiard ball. That's it. But then, everything changed. Towards the end of the 19th century, a series of experiments completely shattered that simple picture. Scientists found out the atom wasn't the end of the line at all. No, it was actually made of even smaller, more fundamental pieces. The uncuttable had been cut. So let's meet the new players in the game. First, you've got the super tiny, negatively charged electron, found by J.J. Thomson. Then there's the much heavier, positively charged proton from Rutherford. And finally, the neutral neutron, discovered by Chadwick. The big deal here is that these three little particles, with their totally different charges and masses, were the clues everyone needed to start figuring out the next great puzzle. Okay, so with these new particles discovered, the race was on to draw a new blueprint for the atom. I mean, if it's not a solid ball, then what in the world is it? How are these protons and electrons actually arranged? Let's take a look at some of the first drafts. So, J.J. Thomson, the guy who found the electron, he came up with the first big idea. He called it the plum pudding model. Just imagine a ball of positively charged goo or pudding, and stuck inside it are the little negative electrons, like plums. In this model, everything, the mass, the charge, it's all just kind of spread out evenly. But then Ernest Rutherford comes along with a totally different and pretty radical idea. He suggested that the atom is actually mostly empty space. You've got a tiny, super dense positive center, the nucleus, and the electrons are orbiting way out, like planets circling the sun. It's a beautiful picture, and it came from a truly game-changing experiment. Okay, so let's break this down, because it's awesome. Rutherford's team basically shot a beam of tiny, positive particles, think of them as microscopic bullets, at a piece of gold foil that was unbelievably thin. Now, if the plum pudding model was right, those bullets should have just blasted straight through. But what actually happened was just shocking. Yeah, most of them went through, but some got deflected, and a tiny handful, like 1 in 20,000, bounced almost straight back at them. Rutherford's reaction says it all, right? The only way a particle could ricochet like that is if it hit something incredibly small, incredibly dense, and with a strong positive charge. And just like that, the atomic nucleus was discovered. The plum pudding model was completely toast. And what this experiment really revealed was just how empty the atom is. I mean, it's almost entirely empty space. The nucleus, where all the positive charge and almost all the mass is packed in, is about 100,000 times smaller than the atom itself. To give you some perspective, if the nucleus was a marble sitting in the middle of a giant sports stadium, the atom would be the size of the entire stadium. So, Rutherford's nuclear model was this incredible breakthrough, but it had one giant, fatal flaw. According to the physics everyone knew at the time, his atom just couldn't exist for more than a split second. So how do they solve this little cosmic problem? So here's the issue. Classical physics said that any charged particle that's accelerating, like an electron whipping around in an orbit, should be constantly giving off energy as radiation. That means it would lose energy, its orbit would get smaller and smaller, and it would spiral into the nucleus in a death spiral in less than a second. Every single atom in the universe should just collapse. But they don't. So why not? The solution came from a physicist named Niels Bohr, and it was completely out there. He basically said the old rules of physics just don't apply down at the atomic scale. He introduced this wild idea called quantization. that energy doesn't come in a continuous flow, it only comes in distinct little packets or quanta. The best analogy is a staircase. You can stand on step 1 or step 2, but you can never, ever stand in between the steps. Bohr took this idea and applied it directly to the atom. He said electrons can only exist in very specific energy levels, or orbits. The lowest step on the staircase, the most stable one, is called the ground state. He labeled it n equals 1. An electron there is perfectly happy. It's stable and it doesn't radiate away its energy. Now, if an electron wants to get to the next level up, the first excited state at n equals 2, it can't just absorb any old amount of energy. It has to absorb the exact amount of energy needed to make that specific jump. It's like an elevator that only works if you pay the exact fare to get to the next floor. And this is where it all clicks together beautifully. When an electron from a higher step, say n equals 3, falls back down to a lower one, it has to release that extra energy. And it does so by spitting out a photon of light with a very specific frequency, which we see as a specific color. And this perfectly explained the unique patterns of light, the atomic fingerprints that scientists had seen for elements like hydrogen but could never figure out. It was a huge win. Bohr's model was a massive success. I mean, it made the atoms stable and explained those mysterious spectra, but the story was about to get a whole lot weirder. Those neat, tidy, planet-like orbits, they were about to dissolve into a fuzzy cloud of pure probability. The next mind-bending leap came from Louis de Broglie. He basically asked, if light can act like both a wave and a particle, hey, maybe matter can too. He suggested that electrons, which we all think of as these tiny little balls, also behave like waves. And this wasn't just a crazy thought. It was proven in experiments where beams of electrons were shown to bend and spread out like waves of water. And that leads us straight to Werner Heisenberg's famous uncertainty principle. This is a fundamental rule of the universe. It says you can't know everything about a particle at the same time. The more precisely you measure an electron's position, the less you know about its momentum, and vice versa. And here's the big takeaway. If you can never know both where an electron is and where it's going, the whole idea of a neat, predictable orbit goes right out the window. It's impossible. So if orbits are gone, what's left? Well, this brings us to the final chapter and our modern view, the quantum mechanical model of the atom. And this is where we trade the certainty of fixed paths for the strange mathematics of probability. See, in this model, we don't have orbits, we have orbitals. And an orbital isn't a path, it's a 3D region of space, a probability cloud, where you're most likely to find an electron. Each electron gets its own unique address, made up of 4 quantum numbers. Think of them this way. N tells you the energy level, or size. L tells you the shape of the cloud. ML describes its orientation in space, and MS tells you its spin. And what is just absolutely incredible is that we can build the entire electronic structure of any atom in the universe using just a few simple rules. The Aufbau principle says electrons are lazy. They fill the lowest energy spots first. The Pauli exclusion principle says no 2 electrons can have the exact same 4-number address. And Hund's rule tells us how they spread out. These rules are literally the foundation of the periodic table and all of chemistry. And that pretty much brings our journey full circle. We started with the simple, solid ball and ended up with a fuzzy cloud of probability, all governed by a few elegant quantum rules. And these rules don't just describe atoms. They predict how they'll bond, why elements act the way they do, the very structure of all matter. It really just leaves you with one final thought. If this model can explain all of chemistry, what other secrets of the universe is it just waiting to unlock?